Hi, everyone. Thanks all for listening in. So today what I want to talk about is how objects move in space. This is a natural extension of what I've been talking about before, which is where things are in space and how they look given our particular perspective. And how things move in space is important for a variety of reasons. To start with, the fact that things in space move in relatively predictable ways is what allows us to send spacecraft to go visit them. So, for example, there is a mission that's about to launch in actually October called Lucy, which has the goal of visiting 5 different asteroids, which are scattered throughout the solar system. This is a diagram of the solar system. The sun is in the center. This is the Earth's orbit. Earth is there. This is Jupiter's orbit. Jupiter is here. This is Jupiter and Earth at one particular time, and a set of 5 different asteroids where they are at another particular time. These are Eurybates, Polymele, Lucas, Orus, and Patroclus, Menelaus. And this green curve is the path the spacecraft plans to take, which will carry it past all of these objects over the course of several years from 2025 to 2033. These are asteroids. They're not particularly big objects. And the fact that this tour and mission exist demonstrates how well we can predict these things, because it means we can have a fairly good idea of where all of these objects are 10 to 20 years from now. Maybe 15. And that's because we have a very good idea of how these objects move, and we can make fairly reliable predictions going forward. So this is the basis of all space missions. If we couldn't know where Venus or Mars or moons of Saturn would be in the future, it'd be really hard to send missions to them, but we can. In addition to kind of that practical value, another aspect of the way things move is that encodes information about astronomical objects themselves. A particularly dramatic example is made by this picture here, which is showing the locations of stars near the center of our own galaxy. And these different lines show the trajectories of the stars as measured over the course of several decades. And what you'll see is they follow nice, happy, curved paths. By tracking the stars in this way, we can actually figure out that there is an object in here that is extremely massive, that is causing these stars to move in a particular way. And we can even say how massive that object is. We know that it's about 4 million times more massive than the sun. And this is the supermassive black hole that lives in the center of our galaxy. And we can figure out its mass and that it's even there by basically how it affects the motion of stars in its vicinity. So this is, of course, all really neat and useful, but then it raises the obvious question, how can we use motions in this way? And the first thing to understand about this is that the motion of objects in space is often simpler than the motion of objects on Earth. We can get motions that look quite complicated. This is the trajectory of the Rosetta spacecraft in the vicinity of a comet. And you might go, wow, that looks complicated. But the actual equations and theoretic and physics that describes this motion is actually simpler than the physics that describes the motion of, say, you or even cars in normal day-to-day operations. The reason that it's simpler to work in space is simply because space is so empty. On Earth, a lot of the complications arise because nothing is isolated. Every object is interacting with a lot of other objects. Whereas when you're talking about space, usually it's only one or a couple of objects that actually map. So we're going to try and see how that works. Now, in practice, doing this involves a lot of really annoying math. But there's a few basic principles that you have to keep in mind. And the number of fundamental principles that control how things move is fairly small. There's basically two big things that control how things move in space. Mostly. There's a few exceptions. There is Newton's laws of motion and the universal law of gravitation. Now, I do want to say one thing up front. Do not overread the word law here. It's not as if there is something that is imposing a legal requirement on space objects and telling them they have to move that way or they'll get in trouble. These are statements about general principles of motion that all objects observationally follow. Do we know why they exactly work the way they do? That's a question for philosophy of physics. For now, all we can say is they seem to apply to a very large range of objects. If you found an object that did not follow the prescriptions in these rules, you would become famous and everyone would be excited. But thus far, that doesn't seem to be the case. So what we're going to talk about this time primarily are Newton's laws of motion. And next time we'll talk more about the law of gravitation. And again, I'll tend to call them rules or tendencies because that gives a better impression of what we're talking about here. Okay, so what are these basic rules of motion from what are called Newton's laws? There are three of them. The first one is that an object will tend to move in a straight line at constant speed unless acted upon by an outside force. The second one is a force is a mass times an acceleration, which at this point you're going, wait a minute, what do these words mean? These words are a bit of jargon, and we'll get into all of them in a bit more detail in this recording. So just be a little patient for now. And the third one is every action has an equal and opposite reaction. Now, those are all saying something, but it's a little unclear what they're saying. And so we need to take a closer look at this because words like what is force, what is acceleration, what exactly is mass, all of this stuff needs to be defined before you can understand what these rules are telling us. And just to say, each one of these rules is tied to one of the questions in your list. So this first rule is tied to the question of why spacecraft don't always have to fire their rockets to move through the solar system. The second rule involves why when you launch a rocket, they often have stages. And the third has more to do with what happens when you try and make two objects interact in space, and also why breaking an asteroid that's heading towards Earth is a bad idea. These we'll talk about in more detail during class period. Okay, but let's look at these rules individually to see what they actually say and get a proper sense of this. Let's start with the first rule. It can be rephrased to be a little clearer. The first rule says that unless an object interacts with another object, it will move at a straight line at a constant speed. Now, that is supposedly a fundamental rule of motion. but it's nothing you have experience with. If you think about any object moving, it doesn't move at a constant speed and very rarely moves in a straight line. You take something in your hand and drop it, it starts moving faster and faster, hits the ground, and then stops. The reason for that is because on Earth, we have lots of things to interact with. We can interact with the ground, we can interact with the air. Specifically, also, there is a giant planet beneath us that is constantly interacting with us and causing trajectories and motion to deviate from this property. It took a long time to realize that this was a natural way for things to move. Because here on Earth, that's not our experience. But if we go in space, we see stuff like this all the time. For example, this is a series of pictures of Barnard's star. It is a fairly nearby star, but what's unique about it is it actually moves through the sky at a fairly decent clip. This is a series of pictures taken over the course of about 20 years. You can see the stars in the background up here don't do much, but this thing is trucking along. And it's moving at pretty much a straight line at constant speed. That telescope I mentioned earlier called Gaia, in addition to measuring the distances to all the stars, it also measures how fast they're moving. And for many of the stars that aren't interacting with other stars, they also tend to do this. They're just moving at roughly straight lines at roughly constant speed because stars are much more isolated from each other than objects in this room. So in space, this often works. And this has important implications. It means, for example, the way spacecraft operate is very different from how, say, vehicles operate here on Earth. Vehicles on Earth, you have to constantly use fuel to keep them going. Even, fairly low friction systems like maglev trains have to do something to usually keep things going. That's not true for spacecraft per se. These are some of the spacecraft that left our solar system called Pioneer and Voyager, and these are all things that are now flying out of our solar system. And the thing about these is these spacecraft aren't carrying fuel that have been continuously thrusting. They just have had encounters with the inner planets, particularly Jupiter, that gave them a push and caused them to start to move out of the solar system. And they've basically are still doing that. Now, they are interacting a bit with the sun, which is causing their trajectories to distort a little bit and slow down a little bit. But the thing is, once they get going, if they're going fast enough, they'll just keep going. This means that it isn't worth keeping fuel. It often isn't worth keeping fuel on a spacecraft. You want to use that fuel to get them going as fast as possible, as early as possible. And this is also useful because it's tied to another aspect of motion. This is the second rule, which is often written as an equation: force equals mass times acceleration. To phrase that more human-friendly, it's to say that a force is just a type of interaction, causes an acceleration, where an acceleration is a deviation from this type of motion in a straight line at constant speed. Now, we have to be careful about defining those things a little bit here, because especially acceleration is something we use in day-to-day language and have specific ideas about what it means. And Acceleration in this context is more general. So let's be a little more careful about how we describe locations, motion, and changes in motion. So we have an object, like say this star here. Its location, its position is given by 3 numbers, which can be specified in terms of a coordinate system. You have a location in space you'll call the origin. Where is that point? It's arbitrary. You can define 3 axes, left, right, and up. Or sorry, left and right, back and forth, and up and down. Those define the 3 dimensions of our normal space. The location of an object is given in terms of 3 displacements. How far you have to go in x, along this axis, how far you have to go along this axis, which we'll call the y-axis, and how far you have to go along the up and down axis, which we'll call the z-axis. These are named different things on in different systems, but it basically means you need 3 numbers to specify where an object is. You can say, and just to say, another way to think about that is you can say how far away the object is from this point, but you also need to specify the direction. And so you specify how far away it is, that's 1 number. You specify the direction, it actually takes 2 numbers. One is how close is it to up and down, and the other is where is it in this direction versus this direction. So there's fundamentally 3 numbers that tell you where an object is. There's also 3 numbers that tell you how an object moves. One of those numbers is how fast it's moving. This is what physicists call speed. And that more or less matches our experience. If something's moving fast, it has high speed. If it's moving slowly, it has low speed. But if you really want to specify how it's moving, you don't just need to say how fast it's going. This arrow tells us that. But you also need to tell us what direction it's moving, which in this case is moving down and slightly in one other direction. That again requires 3 numbers. You need to tell it whether it's moving upish or downish and how much are you moving, say, this direction versus this direction. So the way something moves isn't just specified by its speed, but by its speed and direction. And that is what is called velocity. In common parlance, velocity and speed can kind of be used interchangeably. In physics and astronomy, we try to keep them separate, even though we will sometimes mess it up. Now, the thing is, if your velocity is constant, not just your speed, but your velocity, then the direction you're moving never changes, and you follow a straight line. Furthermore, since how fast you're moving never changes, you also move at constant speed. So if you have a constant velocity, that's that natural state of motion specified by the first rule. A deviation from this is what is called an acceleration. A change in the velocity. Now that can be an object speeding up or slowing down, or it can be an object changing its direction of motion. This is a picture showing the trajectory of a spacecraft from a cover of a scientific journal that focuses on these sorts of changes in motion. So a change in motion over time is called an acceleration. Now, the thing is, this is a very generic thing, whereas what we often call acceleration is a more specific type of this. So for example, we have an object here and it's moving from left to right, and the arrow indicates how fast it's moving. So it starts off moving kind of slow, speeds up, and gets faster. This corresponds to what's called an acceleration, and this makes sense. It's going faster, it's accelerating. Now, we can more say, in addition to the fact that it's moving, its motion is increasing in this direction. The velocity went from being a short thing to a long thing. So we can even define another arrow that indicates how the velocity changed. This is what is called the acceleration vector. It's just an arrow pointing in the direction that the velocity, the way it's moving, changed. And in this case, the acceleration is in the same direction as the motion. This is what most of us think of as acceleration, but it doesn't have to work like that. For example, here's an object that's moving fast, but slowing down. Now, most people would call this deceleration, but it's still just a change in the motion, going from fast to slow instead of slow to fast. This is also a type of acceleration. But in this case, since the vector, the velocity got smaller, the speed got smaller, the way the velocity changed was like this. It points in the opposite direction as the object's moving. Okay? And you can even get weirder things. You can have an object that's moving at a constant speed, but changing direction. In this case, it's moving up. In this case, it's moving down. What this means is that the change in the velocity, the change in the way the object's moving, points down. So this is also an acceleration. It's just an acceleration that points orthogonally to how the object's moving. The thing is, the only way you can do this stuff is by having the object interact with another object. And that interaction is what is called a force. There is something that causes an acceleration between two in an object. That requires an interaction, and that is referred to as a force. So this equation, force is mass times acceleration, says that the force, which is a measure of the object's interaction with another object, is this quantity called the mass of the object, which is a measure of how much stuff it has. It's a quantity intrinsic to the object that is experiencing this force, times its acceleration, a measure of how its velocity changes. So force, like acceleration, has a direction associated with it. And another way to phrase this that I think is a little clearer, the acceleration an object experiences, how much its motion changes, is given by the ratio of the force applied to it to the mass it has. So that means if an object is accelerating, moving faster, there is a force, an interaction with another object that is pushing it in that direction. If an object is slowing down, there is a force acting on it that is basically applying a force in the opposite direction of motion that is causing it to slow down. This is important to understand because if you apply both of these forces, they could cancel out and the object wouldn't accelerate. This is actually an important thing to keep in mind because we're not always used to ideas of things canceling. The idea that if something isn't accelerating, it's experiencing no force is not quite true. It might be experiencing forces, but those forces are exactly canceling. This is often what we do in lab experiments when we want to show this. We can't make a system that has no forces on it because we're feeling the Earth's gravity, if nothing else. But we can apply other forces that balance it out and make it more or less work. Okay? So that's one thing. Interactions don't have to, can not just add together, they can oppose. And another example of this is objects moving in a circle. In an object moving in a circle, the acceleration is always inwards. It's always orthogonal or at right angles to the motion. So the acceleration, the change in motion points inward. The force, the interaction with the other object must point inward. And it does this no matter where it is. This is what gravity does. You can have a very strong object here that applies a force that always points towards the central body and create a circle or an ellipse. Now, the other part of this equation is this thing called the mass. At this point, all mass is a quantity intrinsic to an object. Some objects are low mass, some objects are high mass. That affects how they move in respect to a particular force. So here we have two objects. One of them is low mass, small. One is high mass, big. If I apply the same force to both objects, since the force is the same, but the mass of this is smaller, it accelerates more. If mass gets smaller, acceleration has to get bigger. So this starts moving quickly. This thing, though, is a higher mass. So you apply the same force, the mass is higher, the acceleration must be lower. So this moves less. This is often something we can kind of get a sense of. If you're, one example of a force is a push. When you push on something, you're applying a force. If you push on a piece of paper, you can get that paper moving quite easily. If you push on a dump truck, you're not going to get it moving very much. This is basically that state. Okay. The last of the three rules, which is very important, is often expressed as every action has an equal and opposite reaction. But that has a very specific meaning. The specific meaning is that if one object exerts a force on the second object, then that second object exerts the same force on the first object in the opposite direction. So if you push on a wall, the wall pushes back on you with the exact same force, but just pointed in the opposite direction. So if object 2 feels a force from object 1 and it's pulling it inwards by this amount, let's be clear about that, applies if object 2 has a force applied to it due to this bigger object, object 1, and this is the size of that force, object 2 applies the same force to object 1, but it points in the opposite direction. So if you grab something and throw it across the room, you have applied a force to that object because you started it to move. You pushing on that object and making it move applied just as much force to you as you did to it, which doesn't sound right because that object went flying across the room and in all likelihood you didn't go flying across the room in the opposite direction. The key reason, and this is the reason force exists as a concept, is the forces are the same. That doesn't mean the accelerations or changes in motion are the same. Let's do a very specific example of this. Imagine I'm standing around and then jump up. If I jump up, I'm accelerating. I am pushing off the ground is pushing on me and causing me to accelerate. The ground exerted a force on me enough to make me start to move. But by the third law, I must have pushed on the ground just as hard and tried to make it move in the opposite direction, which is down. Now, that's true. Our forces were the same, but the accelerations were not. They're actually radically different. The whole thing is the forces are the same, but that's the mass times the change in velocity. That has to equal Earth's, the entire Earth or the entire ground's mass times the velocity change of Earth. Earth's mass is way bigger than mine. So this is going to be an interesting calculation. So say the person weighs 100 kilograms to make it simple, and say that they changed in velocity by going from at rest, from not moving to moving at 1 meter per second in a second. That gives you a change in velocity of 1 meter per second in a second times 100 kilograms. Now we have to turn that into what the change in the motion of the Earth is. And to do this, we have to again use this scientific notation thing. The reason being, because we're going to be talking about the mass of Earth, which is a very big number. And again, the way this works is instead of writing out tons of zeros, we write out 10 raised to some power. And this basically gives you the number of zeros. The reason I'm mentioning this is Earth's mass is 6 times 10 to the 24 kilograms. So 6 followed by 24 zeros, which is very annoying to write. So, but what's important is it's 6 times 10 to the 22 times bigger than the person, and say me. This is a very big number. It's 6 followed by 22 zeros. So the change in velocity, so if this is 6 times 22 times bigger, this has to be 6 times 10 to the 22 times smaller, which means that the change in velocity is 2 times 10 to the minus 23 meters per second in a second. That's undetectable. So even though every action has an equal and opposite reaction, that is, the forces are the same, the way that affects their motion is quite different. Any person jumping up and down doesn't strongly affect the motion of the Earth because the Earth just has that much more mass. And now this gets more interesting if your two objects are closer to the same mass, such as and again, what's nice in space is we can have individual objects interact, like objects just interacting with another object. This is a picture of Pluto and Charon. Pluto is an object in the outer part of the solar system, and it has a pretty big moon named Charon. And what you're seeing here is how they interact. The moon is going around in a circle. That's due to the gravity of Charon, which is pulling it inward, causing it to move around in a circle. like we talked about before. But if the moon feels a force due to Pluto, Pluto must feel a force due to that moon. So it is also being pulled around in a circle. It's a smaller circle because Pluto is more massive than Charon, but that motion is there. And we can see this elsewhere. We can see stars moving in response to the planets that orbit them. Even in our case, Earth does move in response to the gravitational pull of our own moon. So this does happen, and we can demonstrate it in space fairly easily. We can also demonstrate it on Earth, but it's a little trickier. Okay, the final thing I'll mention is this last rule does imply something about motion. There are certain types of motion that are literally impossible. And this is expressed in terms of things called conservation laws. The one I'm going to focus on for this particular section is conservation of momentum, which just says that an isolated system cannot just start moving in one direction. So momentum is just a thing, a quantity, which is the mass of an object times its velocity. Now, if you have an object at rest, like this ball, it doesn't have any velocity, so its momentum is 0. If you then imagine a chunk of that object launches itself off the rest of the object, and this thing stays completely fixed, then part of that object is moving and the rest of it isn't. So now it has a momentum. This is not allowed. You can't do this. And the reason you can't do this is it violates the third law. Now, if you could do this, you would be rich and you could become rich and famous, but thus far nobody's figured out a way to do it. What happens instead, since every action has an equal and opposite reaction, is that if this part of the object starts moving to the right, the rest of this object has to start moving to the left, so that the total momentum, the total amount of motion, or total momentum is 0. Just to put it a different way, if you have an object coming in to another object and then they stick together, this cannot come to rest because this originally had some momentum. So after the two objects interact, it has to keep moving in one direction, in the same direction. This is an important consideration for a lot of different things. Because in particular, asteroid safety. There are a bunch of asteroids in our solar system, and some might occasionally get close to Earth. One thing you might naturally say is, why don't we blow it up like all of the movies say? The movies usually get around that. But that actually doesn't really work. If an object is moving in one direction and it breaks up into different pieces, the fact that every action means every action has an equal and opposite reaction means that as those two objects move apart from each other, that doesn't delete the overall motion. So if something is moving in this general direction, you could break it up and it'll move in different directions, but it's still kind of coming towards you. This is one of the reasons why blowing up asteroids is not the best way to deal with them if they're getting close to Earth. This is a cute graphic from Los Alamos National Labs. If you launch a rocket and blow up an asteroid that's coming towards Earth, you have things that spread out, but now you have, instead of one thing coming towards Earth, you have a whole bunch of things going towards Earth, which is not necessarily an improvement. What you need to do instead is apply a new force to this object to change its entire trajectory, which can be done in a variety of ways. Now, there are other important conservation laws which we will cover, including particularly the conservation of energy. But hopefully this gives you a sense of some of the basic rules of motion that all of these objects have to follow, that all objects in space should follow, or we strongly expect them to follow. And now we need to talk a little bit more about what are the actual interactions. And so next time we will talk about the forces that arise from when objects interact gravitationally. Thank you very much for your time and attention.